A good day to the examiner, Dr. Nick, and my supervisor, Dr. Royal. I am Catriona Ng Choyen from Chemical Engineering, and today I will be presenting my defense proposal for final year project. The title of my project is Technoeconomic Analysis of Low Pressure Membrane Filtration for Microalgae Concentration. The contents of my presentations are broken down to introduction, literature review, and methodology, but I will also talk briefly about some recent collected data. Microalgae are single-cell microbes, usually found in saltwater or freshwater. They produce biomass using photosynthesis. There are four main categories of microalgae, which are diatoms, green algae, blue-green algae, and golden algae. They are rich in carbon, which is why they are widely used in the industries of biofuel, health, pharmaceutical, cosmetics, wastewater treatment, and atmospheric carbon dioxide mitigation. One advantage of using microalgae is they grow very, very fast and have high productivity. They can be harvested throughout the year, giving regular supply, therefore meeting global demands. Algae harvesting is the separation of algae from their growth medium. There are three types of methods, which are electrical, chemical, and mechanical. But most research state that mechanical methods such as coagulation, flocculation, flotation, filtration, and centrifugation are better as they are more reliable and they give higher yield. Membrane process is pushing the culture medium of microalgae through membranes using either gravitational, pressure, or vacuum forces. This makes the algae into a thick paste and therefore obtaining a concentrated product. Membrane technology is a simple physical separation process, widely used in wastewater treatment, biotech, pharmaceutical, chemical, and energy fields. It is a simple operation that is easy to scale up, uses low energy, and rarely uses chemical reagents. In terms of harvesting microalgae, they are usually used in closed or semi-closed photobioreactors or PBR systems to improve the efficiency of cultivating microalgae. There are two types of membrane photobioreactors, which are carbonation, used to improve carbon dioxide delivery to the medium, and retention, to separate the biomass solid from liquids. One of the main problems that is usually found in microalgae harvesting is fouling, which is a deposition of microbes and organic matter on the membranes. It is bad as it can reduce overall performance, decrease flux, consume a lot of unnecessary energy, and decrease membrane lifespan. Because it decreases membrane lifespan, it increases maintenance and operating costs due to frequent cleaning and replacements, which is why recently gravity-driven membranes have gained a lot of attention. It is a low-energy separation process that uses water gravity as its main driving force, which is why it can operate at a stable flux without needing much cleaning or replacing. There are three problem statements that I can draw from this topic. The first one is majority of the cost is lost to issues related to membrane fouling, such as cost for cleaning, maintenance, and replacements. Most of the available research focus on how to control fouling instead of how to optimize the system parameters to reduce the chances of fouling. Also, there are very limited techno-economic analysis studies that are available that focuses only on filtration process. There are three objectives that I wish to achieve by the end of this project. The first one is to collect enough information from literature about membrane filtration, and from that to develop a thorough techno-economic model, and after that, finally, to conduct a sensitivity analysis. The feed of the feed is Flora vulgaris species, which is a type of green algae, and the filters used are microfiltration membranes. In the experiment, transmembrane pressure (TMP) is varied, and the assumed capacity is 10,000 ton per year biomass with a feed of 1 gram per liter. Now we will talk about the literature review. The first technoeconomic analysis focuses more on using air-assisted backwashing, and the next one focuses more on which method should be used to harvest microalgae, giving like the least amount of money spent. The third analysis focuses on a microalgae biomass production plant in Italy. And the fourth one is a techno-economic assessment of the growth systems. The fifth one is not an actual plant, but it is only a hypothetical plant where Aspen software is used to determine the parameters. And the final analysis is to study based on 3 types of cultivation systems. Overall, it can be said that the available studies rarely focuses on filtration process alone. This is the workflow that I came up with for this project. The first one being literature review, and from that, compare available methods. After that, experimentations are performed to collect filtration data at different pressure, where the performance of each filtration is analyzed. Once the data are collected, the power and energy consumption are calculated, and the values will be used to calculate capital costs and operating costs based on assumptions, the assumptions which I will talk about later. From that, a techno-economic model is developed, and parameters that heavily influence the overall cost are determined. And finally, sensitivity analysis will be performed to see how to reduce overall costs. These are the assumptions I came up with for this project. The annual production scale was set up to 10,000 ton per year biomass with initial dry weight of 1 gram per liter, and it will be concentrated to 5 gram per liter. The capital costs are costs that involves harvesting, like equipment costs. Land and factory building costs will not be included. And operating costs are costs involving energy consumption and labor costs. The machines for membrane filtrations are assumed to have a lifespan of 20 years with the cost of $10,000 per unit, while the membranes would have a lifespan of 5 years with the price of $50 per meter square area. In Malaysia, electrical costs for businesses is about $0.103 per kilowatt hour, while water costs for infrastructures are 33 cents per 1,000 liters. These are the data collection done by another student who is also under the supervision of Dr. Royal. And from here, the specific energy used by liquid pump and the energy used in aeration can be calculated. These are the equations used by that student to calculate the values, but the main data that I'll be focusing on would be the work done by pump, the pump power, and the overall energy. The data shown here was collected by that same student, and it is quite obvious that the data collection for cross-flow velocity is still ongoing. But once it is done, we can use the data shown in the previous slide to calculate the energy use. Now, there are 2 types of situation going on. One is membrane modules without aeration, and one is aeration. Aeration is the bubbling on the membranes that is used to reduce the occurrence of fouling. Without aeration, the energy used is purely the energy used by the liquid pump. But when aeration is involved, it would be added with the energy used by the aeration pump. Now, based on the data shown, it can be said that with aeration, more flux is produced, which is a good thing. But the downside is it uses more energy. So the aim of the techno-economic model is to somehow balance or optimize both flux production and energy requirement, while minimizing the overall production cost. And that is all for my presentation. Thank you for listening. I look forward to answering your questions soon.